Hello everyone. This is stress strain section. Okay, and in this video we are going to show you the calculation of shear stress. And in previous video we have introduced the normal stress calculation. Okay, so in this video I'm going to show the shear stress calculation. And shear stress, as we talked about shear stress before, okay, the definition of the shear stress is the shear force divided by area. And in this textbook, the textbook use tau to represent the shear stress and use sigma to represent the normal stress. Okay, and this example, for example, if I have a block here and put on these two support, if I apply a vertical force here, okay, these two cross section will have the create a shear internal shear force. I will create an internal shear force to make the whole system static. Okay, the cross section AB and cross section AC. Okay, these two cross section like here. Okay, like here, you'll create a vertical force here and here, and to balance the force, balance the external force. And yeah, if you can use the force balance, so the force must be to equal to 2V. Okay, because the force balance, everything is static in this course. Okay, and the shear stress, yeah, because you look at this force, this shear force, the force is lying on the plane. Okay, so the V divided by A is this here. Okay, the area of it is here is A. Okay, you will get the shear stress. Okay, and in this textbook, there's another terminology called shear stress equilibrium. Okay, shear stress is equilibrium. So what is shear stress equilibrium? Okay, it's just the same concept like the ridge body extension of the ridge body equilibrium. Okay, suppose we have a material and then we just cut a small piece of this material. It's cut and cut this more specifically. We cut a small cubic of this material. Okay, small cubic of this material. Okay, and we apply a shear force on this cubic. There is this small. We apply the shear force on this material. So this small cubic material will experience the shear stress, right? Okay, the shear stress, right? Okay, shear stress. Okay, if I apply a shear force here, we will have a shear stress. Okay, and because the because in this course, yeah, once again, this course everything is static. So static means no translation and no rotation. Okay, so this element here, this small element here, you will have experienced shear stress here. So there must be a force balance this shear stress. Okay, so there must be a force here to balance this force. Okay, or this small element will have a translational motion. Okay, but everything is static, so there are no translational motion. So there must be a force shear stress balance this shear stress. Okay, but this shear stress and this shear stress, it will create a moment. Okay, it will create a rotational moment. This stress, this stress and this force will create a rotational motion. Okay, but like we always say, this course everything is static, so no translation and no rotation. So there must be the force on this element to create a counter. Okay, this is a clockwise rotation. There must be a this there must be some force to create a counterclockwise rotation to balance this moment. Okay, so this here, so that's why there will be this force here, this force here. Okay, to balance the moment created by the purple force. So the blue force will create a counterclockwise rotation, purple force and create a clockwise rotation, and they will balance to each other. Okay, so in this situation happen, it's called a shear stress equilibrium. Okay, all four shear stress must have the equal magnitude and be directed. either tower or away from each other at the opposite edge of the eminence. Okay, yeah, that's the word description of the shear stress equilibrium. You see, equal magnitude and be direct either tower or away. Okay, either tower is here. This arrow and this arrow point to each other, point together. This called direct either tower. Okay, or it's away. Away is here. Away is here. Okay, tail for tail is away. Okay, head to head is tower. Okay, head to head, away. Tail, sorry, tail is away, and head is tower. Okay, equal magnitude and be direct either tower or away from each other. Okay, at opposite edge of this element. Okay, so that's called shear stress equilibrium. Okay, just extension of rigid body equilibrium. Everything static, no translational motion and no rotational motion. Okay, and here in the textbook, it use a lot of example for boats. Okay, boats. It makes a lot of example on boats and use and calculate shear stress on boats. Okay, and yes, that's really the most simplest example to share most simplest most simple example for the shear stress. Okay, and here is the example 7.9, but I think it's 7.9. The graph has make a very good explanation. I think in this problem you can see by yourself. Okay, okay, because it explains very well. Okay, and in this video I will show you some calculation on the shear stress on bolt. Okay, because the bolt. Okay, okay, the bolt not only can tie the piece together. Okay, this is a bolt. Okay, this is a bolt and this is a nut. Using the bolts and nuts, okay, he can claim these two pieces. Okay, it looks like it's two iron. Okay, let's claim these two pieces. Okay, okay, clean these two pieces. It use the normal stress to clean these two pieces. Okay, there will be a force. Okay, if you tight this bolt by this nut, it will create the normal stress. I think like this. Okay, normal stress like this to claim to claim these two pieces. Okay, but at the same time, this but there's another. Oh, okay, sorry. But at the same time, both has another function. Okay, it's not only to claim these two material. It only also can resist the shear force between these two pieces. Okay, shear force between these two pieces. For example, there's a in these two pieces there's a contact area is here. Okay, it's called shear plane. Okay, shear plane. Okay, you apply the force here and apply the force here, and these two pieces will have the shear force happening on this shear plane. And the bolt, one of the function of the bolt, okay, one of the function of the bolt is to resist this shear force or shear stress. Okay, I think there's a force here, there's a force here, apply a load here, we use P and K, and then you apply this force P. This contact shear plane will generate a shear force. Okay. For example, this will create shear force. I believe the shear force. Yeah, it depends on which direction you are looking at. I think. Okay, I think the shear force maybe if you we use this as a standard so reference. So let's maybe there's a shear force here. Okay, maybe there's shear force here. Okay, V. Okay, there's shear force here. And if you look at it this way, maybe there's a shear force here. Okay, maybe there's a shear force here. Okay, okay, experience force. Yeah, yeah. Okay, you apply the load here, force here, and apply the force in this way, and there will be a generated shear force in the contact area. Okay, but we will explain in detail in the example. Okay, okay. This just for you. You can have a physical picture of picture of the shear force and shear stress. Okay, uh, and sometimes if your bolt is not strong enough, doesn't have mechanical property strong enough, the shear force will tear the bolts apart. Okay, in this video, you will see if you keep if keep a strengthening or increasing the force F, and finally it will tear the bolts apart. Okay, tear the bolts apart. Okay, and it is the shear force to tear the bolts apart. Okay, okay. This example is because of shear force, not normal force. Okay, it's shear force tear the bolts apart. Okay, so let's see some example for the shear force calculation. Okay, I think okay, I'll start to explain these two example. Okay, these two example. Okay, and okay, in the next video I'll explain the other two example. Okay, okay, and this problem and this video will just explain these two simple example. Okay, it say these two example, okay, the goal is the same. Okay, the goal is determine the largest internal shear force resisted by the bolts, include all necessary free body diagrams. Okay, okay. So in this style, in this picture, look at the picture. Okay, the bolts is here. I hope you can see this. The bolts is here. Okay, this the bolt is here. Okay, maybe it's a little transparent. Okay, the bolt is here. The bolt is here. Bolt is here. This is the bolt. Okay, and here this is a nut. Okay, bolt. Okay, bolts. Okay, he say the determine the large internal shear force. Okay, resist by the bolt. Okay, so and like I just in previous slide, the bolt will resist the shear force. Okay, the bolt will resist the shear force. Okay, and for this problem, let's look at the central part again. Okay, look at the central part again. Okay, for analyze the shear force or shear stress on in the bolt, I think it's better to analyze from the middle part first. Analyze from this middle part first. Okay, so let's do the analysis on this part first. Okay, okay, it's better to have this part first. Okay, and then we draw the field, and then we will have to draw the free body diagram on these three pieces. Okay, and I call this, maybe I call this C. Okay, because this in this graph they call it A, this is B, and so let's call this is C. Okay, so let's start from C. Okay, okay, and another thing I have to address is, okay, the shear force happens on the shear plane. Shear force happens on the shear plane. So in this case, shear plane is here. Shear force happen on the shear plane. This is called shear plane. Okay, so when we want to determine the shear force in the bolt, we only have to consider everything happen on the shear plane. So okay, so in okay, so let's start. Let's start with this. Okay, let's start from C first. Okay, C. We draw this C here. Okay, C here. And this external force is kilonewton. Okay, this is external force acting on C. Okay, and because when you you pull this section, okay, and everything is static, and this rod C has a contact with A, and C has a contact with B. Okay, C has a contact. Okay, the shear plane you have contact here. Okay, so C has contact with A and C has contact with the B. Okay, so when you pulling the C to the right, pulling to the C to the right. Okay, in this part of the C, it will experience a friction from A and B. Okay, it will experience it will experience or subject to friction from A and B. Okay, so from A and B. So the A and B will create a friction force on C. Okay, create friction force on C. So this is the maybe this just you can see this origin of the shear force. Okay, so here is a shear force. Okay, here is also a shear force. Okay, and this two shear force is A to C. This shear force is A to C. This is B to C. Okay, and this shear force is because this force is lie on the plane, It's lie on the plane. Okay, so it's called the shear force. It's called a shear force. Okay, A to C. Okay, I think. Yeah, do I have to write it more detail because it's a friction? Okay, because these two areas contact to each other, so we apply external force on C. Okay, the C will experience a friction from A and B. Okay, the friction on A and B will create a shear force on C. Okay, so this is the free body diagram. This is the free body diagram of C. Okay, and this must be equal. This must be equal and opposite to balance the 6 kilonewton to the right. So it must be 3 kilonewton here and 3 kilonewton here. Okay. Okay, so this is a free body diagram of on C. Okay, in free body diagram, okay, we have to. There's a very important in free body diagram. Body diagram. You must draw the force. Draw the force acting on the body. Draw the force acting on the body you are interested. You are interested into RESTED. Okay. Okay, this is a very small concept, but sometimes people ignore it. Okay, because let me state again: when you draw the free body diagram, you must draw the force acting on the body you are interested. Okay, because right now we are interested on this C. Okay, this is member C. Okay, and then if you want to draw the free body diagram of C, okay, you must draw the force acting on the C. Okay, for example, this 6 kilonewton, yeah, of course, this 6 kilonewton is acting on C, so we have to draw it. Okay, and okay, and also here we just say this where the C is subject to the friction force from A and B. So A to C, A acting on C, okay, B acting on C. So we have to draw this force out. Okay, we have to draw this force. Okay, because these three force is acting on C. Okay, so that's the free body diagram. Okay, that's called a free body diagram. But try to draw the force acting on the body you're interested in. Okay, these three forces is all acting on C. Okay. Okay, so the next, what's it on the A and B? Okay, what's the free body diagram on A and B? Okay, A, I think it's here, and this is the force acting on A, 5 kilonewton, and I draw the C. Oh no, draw the B here. Draw the B here. Draw the B. B, there's a external force acting on the B. Okay, it's acting on. Okay, so okay, okay. So let's talk about the free body diagram on A and B. Okay, and from A and B, so there's also another the concept you know, but you never use it. It's called Newton's third law. Okay, Newton's third law. Action and reaction pair. Action-reaction pair. Okay, action-reaction pair. And action and reaction, they acting on different body. Okay, that's also very important concept, but maybe you are easy to forget. Newton's third law calls the force there must be a reaction. Okay, you have action, there must be a reaction. 作用力 and 反作用力. Okay, but action and reaction, they are acting on different object. Okay, that's very important concept. Okay, but yeah, but you often forget about it. Okay, action and reaction acting on different object. Okay, here we see in previously we say C experience a friction from A and friction from B. So there is a force A acting a force on C, or B acting on force on C. B acting a force on C. Yeah, so these two force they will have the reaction force. Okay, they will have reaction force. They'll have reaction force in equal and opposite direction. For example, the A to C equal and opposite direction. This is C to A. C to A. Okay. And here is a B to C. Okay, there's equal and opposite force here. It's C to B. It's C to B. And equal and opposite direction. Yeah, up we see this is opposite direction and equal amount. Okay, so there's 3kN here. Okay, here and here is action and reaction pair equal and opposite. Okay, so it must be 3 kilonewton and opposite in direction. Okay. So let's learn also another very important concept, Newton's third law, action and reaction. Okay, you have the force A acting to C, so you must be a force C acting to A. Okay, you have force B acting on C, you must be a reaction force C acting to B. Okay, action and reaction pair, and also be careful, action and reaction acting on different body. Okay, this is B to C, this is C to B, this is A to C, this is C to A. Okay, do we finish all the force analysis? We haven't, because everything is static. Everything is static. Okay, so in the C with free body diagram, yeah, it's balanced, so it's static. Okay, no problem. But is it static on A and C? Okay, A and C we see 3 kilonewton to the right, 5 kilonewton to the left. Yeah, it's not balanced. Okay, here 3 kilonewton to the right and this 2 kilonewton to the right. So okay, also it's also not balanced. Okay, because in this system everything is static. Yeah, in mechanics of material everything is static. So there must be some force acting on A to balance this system. There also must be a force acting on the B to balance this system. Okay, so the remaining balance force is, okay, this is 3 to the, so this is 3 minus 5 equal to minus 2. So there must be a 2 kilonewton here to balance the force, to balance the system. And here there must be a force acting on B to balance the system. I think it's 5 kilonewton to the left to balance the whole system. Okay, so we finish the free body diagram on these 3 parts. Okay, and okay, so determine a large internal shear force. Okay, which is large internal shear force? From the 3 free body diagram, we only have the shear force. This is shear force, because it is force acting on the plane. This is a shear force. Okay, this is shear force, this shear force, this is shear force. Okay. Yeah, the other is, I think, is a normal force. Okay, we see the shear force, they're all 3 kilonewtons. So all 3 kilonewtons. So the maximum must be 3 kilonewton. Okay, because everything is 3. So this must 3 kilonewton. So everything is 3. So the maximum value is 3 kilonewton. Okay. Okay, so this is the first example to calculate, but this example just calculate the shear force, not the shear stress. But maybe later we have example to calculate the shear stress. Okay. I want to introduce this example because I want to familiar with the free body diagram analysis on the boat. Okay, yeah, it's I think you haven't done this before, so you have to get used to this this analysis method. Okay, I think you must most of you see this analysis at first time. Okay, so it take a little time to familiar with this analysis method. Okay. Yeah, I think yeah, okay, my original plan is show you 2 example on this video, but I think maybe the video is kind of too long. Okay, I will explain the next question. I will explain another free body diagram on the boat. And the next example is double shear. Okay, okay, double shear. Oh, no. This is already double shear. Okay, this is already double shear. Okay, okay. So, okay, this is already double shear. Okay, next is I think is 1, 2, 3, 4. Okay, quadruple shear. Okay, okay. Just a start video here. So see you in the next video. Bye bye. It's really not that easy, right? Not that easy. Looks easy, but not really easy.